All right, welcome to The Explainer. Today we're going to tackle a subject that, let's be honest, sounds a little scary, but it's secretly the language of everything around us. I'm talking about organic chemistry.
So, where do we even start? Well, our journey begins with learning how to read the stories that molecules are telling us. The story of how they change from one thing into something completely new.
Yeah, it's a huge question, right? But the answer, it's actually pretty simple. All of it is governed by the rules of organic chemistry. Think about it. The phone you're holding, the aspirin you might take for a headache, even the DNA inside your own cells, it's all about how these carbon-based molecules get together and, well, change.
So, okay, how do chemists actually track all these changes? They use something called a reaction mechanism. Now, don't let the term fool you. It's not some kind of magic trick where things just poof into existence. It's more like a really detailed recipe, or maybe a roadmap. It shows you every single step, every turn, every little thing that happens on the journey from your starting ingredients to the final product.
Okay, so if we're going to understand that roadmap, we first need to get to know the vehicle that's doing all the driving. And in the world of chemistry, that vehicle is pretty much always the electron.
And this right here, this is probably the most important role in the entire playbook. Seriously, if you forget everything else, just remember this one thing. Chemical reactions are all about electrons moving from one place to another. That's it. That is the whole game.
You see, molecules aren't just these static little statues. Their electrons are constantly being pushed and pulled around, and that creates a shift in their electrical charge. Chemists have a name for this: electronic displacement. And it's kind of like a domino effect, right? A tiny nudge in one part of the molecule can cause a huge change in how the whole thing behaves. I mean, it's the reason Teflon is so non-stick. Its atoms are pulling on electrons so hard that nothing else can get a grip.
And this image just lays it out perfectly. On the left, you've got a stable molecule. Everything's balanced, the electrons are evenly spread out. It's chill. It's not looking to start any trouble. But then look at the right. Something's happened to push those electrons to one side. Now you've got these reactive hotspots. One side has a bunch of extra electrons, making it a little negative, and the other side is missing some, so it's a little positive. This molecule is now totally primed for action. And these hotspots, well, they're the starting points for our reaction roadmap.
So here's the really cool part. Those hotspots aren't random at all. They're predictable. And if you know where the electrons are likely to hang out and where they're going to be drawn to, you can literally map out the entire chemical journey. So let's see exactly how these hotspots kick off the first step on those roadmaps we keep talking about. What's amazing here is how this boils down millions of super complex reactions into just 3 basic steps. First, it's all about opposites attract. An area that's rich in electrons is going to find an area that's poor in electrons. Simple. Step 2, you got to make a trade. To form a new bond, an old one has to break. And finally, step 3, everything just rearranges and settles down into its most stable, happy final form. And while the little details can get complicated, almost all of these reactions fall into just a handful of main types. You're either adding something new. Think about how they add hydrogen to vegetable oil to make margarine, or you're substituting one piece for another, or you're eliminating a piece to get rid of it, or sometimes you're just rearranging the furniture, moving things around inside the molecule. Pretty much every reaction out there is just a different flavor of one of these 4.
Okay, so that's all the theory, but how does this stuff actually work in the real world, in a lab? How do chemists take this knowledge from a whiteboard and put it into practice? Because let's get real for a second. When you run a reaction in a flask, you don't just get this one perfect, pure product. No way. You get this messy soup of leftover ingredients, weird side products you didn't want, and somewhere in there, the thing you were actually trying to make. So the very first challenge is always cleanup.
And chemists have a whole toolbox just for this, and it's called purification. It's basically the same idea as how they get pure caffeine out of coffee beans. You start with that crude, messy gunk from the reaction, and then you use all these clever techniques to separate things out based on stuff like their size or how well they dissolve. The whole goal is just to filter out all that junk until you're left with only the pure stuff you wanted in the first place.
Okay, great. So you've made something and you've cleaned it all up. Awesome. But now you have 2 really important questions you have to answer. First, did you actually make the thing you were trying to make? And second, how much of it did you get? This is where the analysis part comes in.
And this breaks it down really simply. Analysis has 2 parts. You've got qualitative analysis, that's the detective work. It answers the question, what is this stuff? Is it that new life-saving drug, or is it just some useless gunk? Then you've got quantitative analysis, that's the accounting part. It answers, how much of it do I have? Is the dose in this pill correct? You absolutely need both to know if your reaction was a success.
And that really brings us right back to the beginning, doesn't it? From that tiny little shift of an electron all the way to purifying a final product in a flask, it's all connected. Understanding that step-by-step mechanism isn't just some boring academic thing. It's the key. It's how we go from just watching the world happen to actually creating it, designing new medicines, inventing new materials like biodegradable plastics, literally building our future one molecule at a time.
So I want to leave you with this one thought. We have figured out how to draw the roadmaps for how molecules are built. With that kind of power, what problem should we solve next? You know, what huge global challenges, I'm talking sustainable energy, new cures for diseases, are just sitting there waiting for us to figure out the right reaction mechanism to solve